Astronomers tracking 3I Atlas say it has altered its course, worrying scientists about its close proximity to Earth.
The James Webb Space Telescope has observed unusual patterns from 3I/ATLAS, the third known interstellar object. These readings show features never seen before, sparking debates about whether they reflect natural cosmic chemistry or something beyond human technology. Could this comet hold secrets of alien worlds or something deeper? Join us as we uncover the details behind this discovery. The discovery of 3I/ATLAS. The story of 3I/ATLAS began with a careful eye scanning the skies through the ATLAS survey telescope. This wide-field instrument, built to watch for near-Earth objects, suddenly spotted something unusual. The year was a turning point, because the strange visitor did not behave like the countless comets and asteroids normally tracked. After deeper study, astronomers confirmed that this was not just another icy body from the outer solar system. It was moving on a path that could only mean one thing: it came from beyond. With that realization, the object was given the name 3I/ATLAS, marking it as the third confirmed interstellar visitor after two earlier arrivals. The I in its title stands for interstellar, while the 3 signals its place in a growing but still very rare list. What set it apart most clearly was its orbital path. Instead of circling the sun like most bodies, its path was hyperbolic. This shape revealed that gravity would not trap it. It came racing in, would swing around, and then head back into deep space forever. Its speed was also remarkable. It traveled faster than most local comets, a natural result of being born in another stellar system and then wandering for ages through the dark. This speed and its open orbit became the firm proof that it was a true outsider. When scientists looked closer, they could not help but compare 3I/ATLAS with its predecessors. The first, 1I Oumuamua, was long, cigar-shaped, and puzzling, sparking endless debate about its nature. The second, 2I/Borisov, looked more like a classic comet with a bright tail, yet it too carried the stamp of another star system. 3I/ATLAS carried lessons from both. It showed familiar comet features, but its size, structure, and path still raised questions that made astronomers eager to know more. Each of these visitors matters because they carry stories from faraway stars. They are untouched fragments from alien planetary systems, drifting through space until fate steers them past our sun. By studying them, we gain a glimpse of how other worlds may have formed and what kinds of ingredients fill the galaxy. For many, 3I/ATLAS was not just a frozen traveler. It was a message written in ice and dust, waiting to be read by those who had the right tools. And to read that message, scientists turned to the most powerful observatory humanity has ever launched, the James Webb Space Telescope and its capabilities. The James Webb Space Telescope, often called JWST, is more than a successor to earlier space telescopes. It is a leap into a new era of cosmic discovery. With its giant golden mirror and its instruments cooled to extreme cold, it was built to capture faint light from the most distant corners of the universe. Among its many tools, one shines brightly in the study of icy bodies like 3I/ATLAS, the near-infrared spectrograph, known as NIRSPEC. NIRSPEC is like a translator for starlight. When light from a comet or star passes into it, the instrument breaks that light into a spectrum, a rainbow stretched thin where each color tells a secret about the chemicals present. A dip here or a peak there may reveal water, carbon dioxide, methane, or even complex organic material. It is this ability to read hidden fingerprints in light that makes NIRSPEC so valuable. Without it, astronomers would only see brightness and color. With it, they learn what the object is truly made of. The telescope's strengths go beyond sensitivity. Its mirror is more than 6 meters wide, collecting far more light than earlier instruments like Hubble. This means it can pick out signals that would be invisible to other observatories. Its coverage of the infrared spectrum also lets it peer through dust clouds, uncovering gases and ices that hide from visible light. Most importantly, JWST can study very faint targets. For something as fleeting and distant as 3I/ATLAS, that sensitivity is not just helpful, it is essential. There was a clear reason why Webb was turned toward this interstellar wanderer. Scientists wanted to know its chemistry, its makeup, and its origins. Was it rich in the same compounds as comets in our solar system, or did it carry exotic mixtures from a star we have never seen? By analyzing its gases, dust, and icy surface, astronomers hope to answer these questions. In truth, each molecule detected becomes a clue. Together they form a puzzle that might reveal how planetary systems far away are built and how material travels across the galaxy. Directing JWST at 3I/ATLAS was like pointing a finely tuned ear toward a whisper from another world. The telescope's instruments, especially NIRSPEC, gave astronomers a chance to hear that whisper clearly, promising insights no other observatory could provide. JWST, observations of 3I/ATLAS. On August 6th, in the year 2025, the James Webb Space Telescope was aimed toward the distant wanderer called 3I/ATLAS. This moment was important because the object would only remain in view for a short time before slipping further into the dark. Astronomers knew they had a narrow window to capture as much information as possible, and Webb's powerful instruments were ready for the task. When the first spectra came through, scientists saw clear signals. One of the strongest was the presence of carbon dioxide in the coma, the glowing cloud of gas that surrounds the icy body. Carbon dioxide is common in comets, yet its detection here confirmed that this visitor carried familiar ingredients found within our solar system. Alongside this, there was evidence pointing toward water ice locked inside the nucleus. This detail mattered deeply because water ice speaks to origins in cold and distant regions, hinting at the environment where 3I/ATLAS was born. Beyond these two clear markers, there were faint signs that dust and organic molecules were also present, painting a picture of a rich and complex traveler. But the process was not without struggle. Separating the light from the coma and the nucleus proved challenging. The bright gases could easily cover the signal from the icy heart hidden inside, leaving researchers with the task of teasing out faint differences. Time was another enemy. The comet-like body was moving quickly, and Webb's schedule had to be balanced with other pressing observations across the sky. Every moment counted. On top of that, some of the signals were weak or noisy, forcing scientists to spend long hours sorting real features from simple background interference. Even with these difficulties, the findings left astronomers with excitement. Each faint line in the spectrum added a thread to the story of 3I/ATLAS. The combination of carbon dioxide, water ice, dust, and organics suggested that this was not just an ordinary rock, but a true messenger from another star system. Yet as the data poured in, something else began to stir curiosity. Certain details seemed to go beyond ordinary expectations. These anomalies would soon catch the eyes of scientists and the public alike, lighting up headlines across the world. The anomalies that sparked headlines. Not long after the first data from 3I/ATLAS reached Earth, unusual results began to surface. Early measurements suggested that this interstellar visitor might be larger than many had thought. Some size and mass estimates placed it above the range expected for a body passing so close, raising questions about whether observers were underestimating its brightness or overestimating its volume. This mismatch between what was seen and what was expected gave rise to debates in the community, with some urging caution and others eager to speculate. Adding to the puzzle were brightness fluctuations that appeared in the light curves. At times, the object shone stronger, while at other times, it dimmed unexpectedly. For comets and icy bodies, changes like these can be caused by jets of gas bursting from the surface or fragments breaking away. Still, the irregularity of the pattern led to more questions. Some wondered if the surface was rotating in strange ways, while others thought the structure might be uneven, scattering sunlight differently as it tumbled through space. The trajectory of 3I/ATLAS 3I/ATLAS also added fuel to the mystery. While its path was broadly consistent with a natural interstellar orbit, subtle deviations hinted at forces beyond gravity. Such non-gravitational effects are usually explained by outgassing, where jets of vapor act like small thrusters, nudging the object ever so slightly. Yet each new calculation seemed to spark more curiosity than it answered, leaving many eager to see whether the behavior was within the range of natural comets or something far more unusual. The media played a powerful role in shaping how these anomalies were viewed. Reports highlighted the size questions, the brightness changes, and the odd motion, weaving them into bold stories that captured the public's imagination. To readers, it often sounded like signals of something beyond the ordinary. Headlines spread quickly, framing these details as hints of a mystery that could hold deeper meaning. While scientists urged patience and careful analysis, the wider world was already swept into excitement, with every new observation feeding the sense that 3I/ATLAS was not just a frozen traveler, but a riddle waiting to be solved. And with whispers of mystery growing louder, the next step was to weigh natural explanations against far more exotic ideas, setting the stage for a debate that would test both science and imagination. Scientific explanations versus exotic theories. When the unusual behavior of 3I/ATLAS was first reported, scientists quickly set out to understand it. The most practical explanations came from well-known comet activity. One strong possibility was cometary outgassing. As sunlight warms the frozen surface, gases trapped in the ice begin to escape. These small outbursts can act like tiny thrusters, pushing the comet slightly and changing its path. Even though the force is small, over long distances it can create noticeable effects that explain shifts in motion. Dust jets were also considered. When icy pockets burst open, they can carry dust into space, forming narrow jets that reflect sunlight in uneven ways. These jets can cause the object to shine brighter at some moments and dimmer at others, giving the appearance of strange brightness changes. For astronomers, this is a normal feature of comets, even if it looks puzzling at first glance. Another natural reason may lie in the composition of the body. Comets from our solar system have been studied for decades, but 3I/ATLAS came from a different star system. Its mix of ices, dust, and organic material could be different, making its behavior unusual when compared with local examples. Differences in how it reflects light or how its gases escape could explain the odd features seen in the data. Yet, as with every great mystery, more exotic ideas rose alongside the natural ones. Some thinkers suggested that perhaps 3I/ATLAS was not just a comet, but something made. The thought of an alien probe or an engineered artifact caught attention. Advocates of these ideas, such as Avi Loeb, pointed to the anomalies as signs that the object might be more than nature's work. They argued that unusual acceleration, brightness changes, or size estimates could be signals of artificial design. Most scientists, however, remained cautious. They reminded the world that extraordinary claims require extraordinary proof. Natural processes are known to create strange and surprising behaviors, and without clear evidence, it is safer to look first at explanations rooted in physics and chemistry. While speculation is exciting, science demands patience and solid data. Still, the question lingered: what would a true signal of technology look like if it ever appeared? To answer that, scientists had to define what truly counts as a sign beyond human reach. What counts as a signal beyond human technology? As curiosity around 3I/ATLAS grew, many wondered what would truly separate natural behavior from something artificial. The answer begins with defining what a signal of technology might look like. One example would be radio pulses. Unlike the random noise of space, an artificial radio signal would carry patterns, rhythms, or narrow frequencies that hint at design. Another possible clue lies in isotopic ratios. If materials show unnatural proportions of certain atoms, it could suggest an artificial process rather than natural chemistry. A third sign might be structured light curves, where the way an object brightens and dims follows a precise or repeating pattern more like machinery than ice and dust. But even with its power, the James Webb Space Telescope is not built to look for radio waves. Webb is a master of infrared light, perfect for studying gases, dust, and icy surfaces, but not for scanning the sky for transmissions. This means that while Webb can reveal the chemistry of 3I/ATLAS, it cannot directly test whether it is sending signals. To search for radio pulses, scientists must rely on large ground-based radio telescopes, such as those used by SETI projects. So far, Webb's findings point toward natural comet chemistry. Carbon dioxide, water ice, dust, and faint organics all match what astronomers expect from a frozen traveler. Nothing unusual in the data has demanded an artificial explanation. This does not close the door to wonder, but it reminds us that the evidence we have fits comfortably within the known behavior of comets. Researchers in the field of SETI take a careful approach. They use radio arrays to listen for narrowband transmissions that nature does not produce. They also try optical SETI, which looks for laser-like flashes of light. And just as important, they repeat their observations to see if signals return again and again. This method ensures that what looks unusual is not just interference or a passing glitch. Each step taken adds clarity, but it also adds humility. Finding a true signal beyond human technology would change everything. If no technology is found, why does 3I/ATLAS still matter so much to science and to our place in the universe? Why 3I/ATLAS is still important? Even after the noise of headlines and the storm of speculation, the real value of 3I/ATLAS lies in its science. For the first time, astronomers have been able to study, in detail, the chemistry of an object that comes from beyond our solar system. This is no ordinary comet. It is a fragment of another star system story, carrying with it a history written billions of years ago in a distant place. What makes it remarkable is the clear detection of carbon dioxide, water ice, and organic compounds in its structure. These are not just common molecules. They are the foundations that can shape planets, drive atmospheres, and in certain conditions, support life. To find them in an interstellar body shows that the materials of creation are not limited to our neighborhood, but may be scattered across the galaxy. This knowledge opens the door to bigger questions. If such objects travel freely between star systems, could they serve as carriers, seeding new worlds with ingredients for life? Many theories suggest that comets may have played this role for Earth itself long ago. Seeing water and organics in 3I/ATLAS makes that idea far more universal. It hints at a cosmos where life's recipe is not rare but widespread, waiting for the right conditions to spark. Compared with earlier visitors, this comet adds more layers to the puzzle. 1I Oumuamua was odd and rocky, unlike anything expected. 2I/Borisov looked more familiar, behaving like a classic comet. 3I/ATLAS, however, carries a richer mix with gas, dust, and ice all working together to surprise scientists. Each object is unique, and together they prove that interstellar space is filled with far more variety than anyone first imagined. By studying them closely, we are not only learning about other systems, but also about ourselves. 3I/ATLAS reminds us that our solar system is just one piece of a much larger design, and the secrets it carries will guide research for years to come. Yet while scientists measured and analyzed with care, the public world spun a very different story, one filled with drama, bold claims, and stories that spread faster than the comet itself. Public reaction, media frenzy, and the road ahead. The discovery of 3I/ATLAS quickly captured the imagination of the public. Reputable science outlets focused on its chemistry and its meaning for planetary science, highlighting the importance of carbon dioxide, water ice, and organics. But tabloids took another path. Their headlines leaned toward the dramatic, asking whether the object might be a message or even a craft from another world. Online discussions gave rise to countless theories. Some saw the object as proof of alien technology, while others wove tales of hidden signals. Social media only added fuel. as stories bounced across platforms with little regard for accuracy. In the middle of this swirl, science communicators worked tirelessly to explain the facts. They wanted to keep the excitement alive, but also to remind audiences that what was observed came from natural chemistry and motion. Still, in many places, the loudest voices were the ones selling mystery over truth. Beyond the noise, the work of science continues. Astronomers plan follow-up studies with ground-based telescopes, hoping to trace the comet's light for as long as possible. The Hubble Space Telescope may provide more images, while radio observatories will listen for any patterns worth noting. Yet many questions remain open. How massive is the comet's nucleus? What shape does it hold? How quickly does it spin as it moves? Each answer could unlock new layers of knowledge about how interstellar objects are built. The future brings even larger dreams. Some researchers are designing mission concepts that might one day chase such objects and study them up close. Reaching them is difficult, since they arrive suddenly and move fast, but the potential reward is enormous. Capturing even a fragment would mean holding a piece of another solar system in human hands. For now, time is short. 3I/ATLAS is already on its way out, following its outbound path into the deep. Soon it will fade beyond reach, but the lessons it leaves behind will last. Its brief visit has reshaped how we see our place in the galaxy, and it has prepared us to be ready when the next traveler arrives. If you enjoyed this video, like and subscribe, and also click the next video shown on your screen.